All right, so we should be about right here. Weight hanging from a spring bobs up and down with position function s equals 3 sines t. What are its velocity and acceleration at time t? And the question here, we've already kind of done this, and the third question is what is a jerk? It's actually in your notes above where we did most of this problem. Velocity is s prime. Without looking above, what's the derivative of 3 sines t? 3 cosines t, because the derivative sine is a cosine. So 3 cosines t. All right, acceleration, which I'm completely misspelled, but whatever. Vs double prime. What's the derivative of 3 cosines t? What's the derivative of that cosine function? Negative sine. So negative 3 sines t. And our jerk, which is the pull, or the initial rush of acceleration, has got to be the derivative of s double prime. What's it going to be? Negative 3 cosines of t. Now the question here is, when does that jerk happen? When does that jerk happen? Now this particular question is about something, a weight bobbing up and down on the spring. Okay? So if the spring expands as far as it can down, isn't it going to get jerked right back up? Okay. So this is going to happen where the change in velocity, acceleration, is what? 0. It's going to happen at 0. Jerk's going to happen at 0. So you just take your third derivative and you say equals what? 0. 0 equals negative 3 cosines of a t. We'll then divide out our negative 3. Oh yeah, there's a little trig up here, isn't there? How much did I remember? Anyways. Let me rethink this for a second. I want to make sure I'm teaching it right. It's going to happen at 0. I'm trying to throw y'all off. Just trying to make sure I'm thinking about the right thing. What I was doing is I was looking at the original functions graph. I want to make sure that what we come up with matches this graph. If you look at the original, I'm looking at the original function. From the original function, you ought to be able to tell me where the jerk's at. There's actually a couple of places where the jerk's at. Wouldn't there be a jerk here, 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 and here? You know, think about it. Things going up, and it pauses for a moment in time, and then gravity pulls it right back down, right? There's a jerk there. It's going down to the end of the spring, it pauses for an instant in time, and the spring pulls it back up. There are lots and lots of places where there are jerks, because it's going up and down and up and down and up and down. But what I want to make sure is I want to make sure that our answer matches the original answer based on the original equation. That's why I was looking at the graph. So what I'm going to do is I'm going to find one of these jerks. There's a jerk there at 0, which is no surprise to me, but there's actually more than one answer here. There's going to be a jerk down here. I need to use a minimum function for that. If you know your unit circle, the answer will be pretty obvious. I'm just showing you technology as your friend here. So there's another jerk at pi, 3.14. There's a jerk here at 0. There's a jerk here at pi. Where do you think that jerk's at? 2 pi, okay? So they're multiples of pi. Now, does this answer make sense? What we have written on paper, does it make sense? It says that 0 is the cosine of t. Well, I think my answer may not actually make sense. I don't know. I would fix cosine by taking the arc cosine of both sides and doing it by hand. That frees up t because cosine and arc cosine annihilate each other. Anybody know what the arc cosine of 0 is? It's not what it's not what my graphing calculator suggests. Where is cosine 0 on the unit circle? 90 degrees, pi over 2. 3 pi over 2, right? So the work I'm doing down here is suggesting that that happens at t equals pi over 2 and 3 pi over 2, which I don't think agrees with the original graph. So Milbrath did something wrong. Milbrath does that. It's pi over 2 or 3 pi over 2. If you're watching along, that's not what graph suggests. Did you guys understand when we looked at the graph where we thought the jerks might be? So that's not what my graph is suggesting, which means I did something wrong. My graph is suggesting 0, pi, 2 pi, 3 pi, and so forth. These points where we go from where our position changes direction. We set that thing equal to 0, so we actually found where the velocity went from wasn't positive and negative in this one. This was the position function. Let's take a look at the derivative. The derivative's graph was -3 cosines of x. Is this still suggesting the jerk's hand in the same place? There's a jerk at 0 pi, isn't it? There's another jerk. Where's that at? Pi. There's another jerk. 2 pi. Another jerk. Where's that at? 3 pi. So why isn't my math suggesting that? That's the real question. I don't even remember if I intended for a kid to do this thing with calculus, to be honest with you. I may not have. We said it equals 0. Arc cosine of 0 is pi over 2. 3 pi over 2 and so forth. I guess we just have to support it from a graph. can't think of another way to do it. So from the graph of -3 cosines of t times r 0 pi, pi, 2 pi, and that pattern goes on forever. That's when the jerk happens. Kind of weird to measure time in pi, isn't it? You're not really, it's 3.14 seconds, 6.28 or so forth, but it's just perfect. That's how you do it by hand. Yep. Took me a second. I remembered how. All right, if you want to do it by hand, you have to understand your form. This is S equals 3 sines of t. That's the original equation. The 3 is units above or below rest. Okay, units above or below rest. Now, these jerks, rest being the origin, these jerks are happening 3 units above and 3 units below. Okay, so what you actually have to do is you have to say 3 equals -3 cosines of t, if you want to do it by hand. Because that's where the jerk is happening if you use it supported by the graph. So I'll solve that one with you because you haven't done trig in a minute. And I don't know, geometry seems to be a weak skill for y'all. What would you divide out? -3. I swear to you, this is a geometry standard. I swear it is. I taught that for us. -1 equals cosine of t. What's the opposite of cosine? Arc cosine. So what you do is you take the arc cosine of both sides. And that frees up 2. Now, the arc cosine of 1 is saying where on the unit circle is x1? And then 0 pi, 0 pi, 2 pi, and so forth. 0 pi, 2 pi, and so forth. Now, that doesn't count for everything, because the reality is this is actually a plus or a minus 3. Because we're 3 above, we're 3 below. So at the same time I'm finding the arc cosine of 1, I also have to find the arc cosine of the negative 1 as well. And that gives you your pi's. Okay? That's how you do it by hand. Here's a little trick. I really think your book just says look at the graph on that one. I don't think it suggests you do much else. I think it suggests you analyze graphs. All right, here's the derivatives of the other trig functions. You get to add, let's see, you're up to 7 now because you have the derivative of sine and cosine, and you're about to add a couple. This is going to be fun. All you know right now is the derivatives of sine and cosine. Rewrite tangent in terms of sine and cosine. I gave you like 5 or 6 of these quizzes. Rewrite tangent in terms of sine and cosine. Yes, ma'am. 9x over cosine x. So your job isn't actually to find the derivative with respect to x of tangent of x. Your job is to find the derivative of x with respect to x like sine x over cosine of x. Well, what rule is that? Quotient rule. Okay. Anybody remember the quotient rule, or have you already forgotten it? G of x f prime of x. You don't know this, you should probably write it down. This one's locked in place. The second one doesn't matter. One's prime, one's not. The one that hasn't been prime yet.
Prime of x, f of x. All sitting over? U of x all squared. I'm going to have to erase that because I'm in the room, but if you didn't know it, you should probably write it down. Because that's how you memorize, kids. You didn't write it, you say it. They say if you can read something 7, write something 7, and say it's 7, you have about a 70% chance of remembering it for a very long time. I like that. That's 777, good number. I wonder what 666 does. I don't know. I'm sure the devil was pretty good at math. I always figured God was omnipotent, which means all-knowing, because he was extremely good at math. Because he knows your equation, he knows my equation, he knows how those equations will interact with each other. I always figured that if the devil had enough balls to challenge God, he had to be pretty good at math too. Or she is Lucifer, right? Lucifer. Described as the most beautiful creation ever. I'm describing a male or a female. That's beautiful. You don't say that's a, oh my God, that's a beautiful man. I don't know, maybe girls do. You say that?
Personally.
Probably not.
Probably.
Beauty is a description. It's still guy to female. It's feminine. So anyways, I had to erase the rule. It's going to start off with cosine of x times the root of sine. Cosine of x. Take away sine of x times the root of cosine. What's the root of cosine? Negative sine of x. All sitting over cosine squared of x because we're doing square of the bottom piece. Cosine times cosine and cosine squared. We don't put it over the x because that causes confusion. I think you're actually squaring the x. We'll put it right there with cosine. So the top is kind of unique. We'll have a cosine squared of x, a minus times a minus, plus what? Sine squared of x. Sitting over a cosine squared of x. Now, from your three Pythagorean identities, what is cosine squared plus sine squared? 1. Oh, we're almost done. What's 1 over cosine from your trigonometric quizzes? Secant. What's 1 over cosine squared? Secant squared. So the derivative with respect to x of tangent of x is secant squared of x. I really need to introduce something else. dx. That does need to be introduced here. dx matters. We're about to do the chain rule them this week too. So dx, secant squared of x dx. All right, well, that was tangent. I guess cotangent's up next. We're going to do the same thing. We're going to rewrite it in terms of sine and cosine. So cotangent would be cosine over sine. Any issues with that? What rule are we going to get with it? Quotient. So we'll take sine of x. We'll multiply it by the derivative of cosine, meaning negative sine. We'll take away from that cosine of x, multiplied by the derivative of sine, which happens to be cosine again. I don't know why I had that last one wrapped in so I couldn't see what I do. Sitting over sine squared of x. All I did was plug in the quotient rule. You guys understand that? By the substitution of the quotient rule, put the derivatives of the respective pieces, and then we'll simplify. So we have a negative sine squared minus a cosine squared, sitting over sine squared. Anybody got any issues with that? A negative sine squared minus cosine squared, sitting over sine squared. That top piece looks oh so close to something. If only those two things are positive. Well, how do you make them positive? Well, at a -1, right? Elizabeth, what's sine squared plus cosine squared?
Tanner, what's sine squared plus cosine squared? 1. It's 1 all day long. So we have a -1 times a 1 up top, which is just -1, and it's sitting over sine squared.
What's 1 over sine? Cosecant. So 1 over sine squared must be cosecant squared, but it's right. Ooh, you're up to 8 derivatives now.
Yeah, it needs a dx. They all need a dx. Every single thing you have needs a dx. We'll revisit all that when we talk about the chain rule, but every single thing you have needs a dx. I don't know why I forgot to put it. Your book doesn't put it in on the first couple. I know better than that. I just forgot to put it in myself. There's always a dx attached. Oh, yay, more of these. Secant's up next. How do you rewrite secant? 1 over cosine.
And whether you like it or not, that's quotient rule. Because that's a fraction. All right, so the top would be cosine of x times 0, right? Minus 1 times negative sine of x, sitting over cosine squared of x. So it actually turned out pretty cool. That's just sine of x over cosine squared. I'll let y'all catch up. Let's see what my wife wants.
Got any ideas what we can do with that?
No! What the deuce you mean? All right, well, please accept this in your heart. This is sine of x times 1 over cosine squared of x. That makes sense? I could break it apart like that? Well, what's 1 over cosine squared? What is it? Secant squared. I don't like the way that looks. I really don't like the way that looks. That's secant squared sine of x, which is not direct derivative. There's a way to rewrite that better. I don't like the way that looks. It's not direct derivative.
We didn't do anything wrong. It just needs to be rewritten. I'm having moments here today. Oh,
I'm getting on y'all. It's a lot better if you break it apart like this. There's nothing wrong with what we did. It's just not the typical rule you memorize. We're going to have the right thing. It's just not the typical rule you memorize. Break it apart like that, and this is the rule that everybody memorizes. What's 1 over cosine? Secant. What's the secant of x? What's sine over cosine? Tangent of x. The other one doesn't have a good ring to it. What did we have? We had sine of x, secant squared of x. That's what we're going to end up with, right? Sine of x, secant squared. It doesn't have a good ring, but it is equivalent to secant of x tangent of x, which sounds a heck of a lot better. Yes. Just broke it apart one. One more, I think. Then we'll get through these things. The derivative with respect to x of cosecant of x will be 1 over sine of x. And we just do the quotient rule again. I know how fun this is, but if you see where it came from, maybe it's Julie at least will like it. That would be sine of x times 0 minus 1 times cosine of x. Sitting over sine squared of x. That's just plug in the quotient rule. So we'll have negative cosine of x sitting over sine squared of x. And I think we'll break this one apart the same way we did the last one. We'll pull out a 1 over sine. We'll pull out the negative 2. And we'll leave it as cosine of x over sine of x. Because that's the way it's actually written. 1 over sine would be cosecant, and cosine over sine would be cotangent. So we have negative cosecant of x, cotangent of x, dx. There's other ways of saying the same derivative. It's just these are the accepted ways of saying it.
now instead of pulling out a sine, I could have pulled out a cosine and had something like cosine of x, negative cosine of x, cosecant squared. It's the same exact thing. But these are the way they're taught. Because they sound better. For no other reason. Of course, to y'all they sound like crap, don't they? Bunch of confusing big words. And I get that. I really do. And it only works if you memorize them. All right, find y double prime if y equals a secant of x. All right, so we scan through our notes. What's y prime going to be? Secant x tan x. Straight out of your notes.
You got it memorized, even better. Add that you haven't memorized yet. So our prime is secant of x, tangent of x. And don't worry about the dx right now, because x is really simple. When x is something like x squared or 3x or 4x, you got to worry about it. Just belongs in forms. So secant x tangent x. How do you find y double prime? What rule? Product rule, right? You have to invoke the product rule. All right, so y double prime would be, in order's not too big of a deal here. I'm just going to take the derivative of secant, which is secant of x tangent of x. Isn't that the derivative of secant? What's the derivative of tangent? Which one is it? Secant squared. There's a plus sign. I already took the derivative of secant, so I don't have to do it again. I'm sorry. Why did I take the derivative of tangent? I did strong. I already took the derivative of secant, so I don't have to worry about it again. Here I have to take the derivative of tangent, which is secant squared. See what I missed that? Sure, I caused some confusion on her side. There's a lot going on there. There is a lot.
What's going on in my head is that I know the rule. I'm following the product rule here. Derivative with respect to x of some f of x times g of x. And I did f prime of x, g of x, plus f of x, g prime of x. Which may not be what you wrote down on your piece of paper, but it's the same thing. It really is. And I let f of x be secant. I made f prime of x secant x tangent of x. I let g of x be tangent. It makes g prime of x secant squared of x. I just did that, okay? About the only thing you should probably do to this thing is clean it up a little bit. There are some things you can do with it, and it should be done. If you distribute that tangent in, you'd have secant of x tangent to what power? The second. Plus secant to what power? The third. All right, you can actually do some more of that. Both of these pieces contain what? Secant. So you pull that secant of x, use a hard bracket here, and you're left with tangent squared plus secant squared. Come on. There we go. Close the hard bracket. All right, now it's been a while since I've done these, but I can make this thing look just a little bit nicer. Maybe, maybe not. What's tangent squared plus 1? That's secant squared? Yeah, it really wouldn't gain me anything. That's a good stopping place, actually. Just show the factorization. That's about as nice and pretty as you can make that thing. All right. Lots of fun there. Hey, you're done. Finally, right? How many of you guys have actually drawn something? Really? No, I mean, tomorrow's the day I'll help you. I'm not going to go over your homework tomorrow. Not tomorrow. Said I was going to help you on your project.
I have a question. Our hyperbolas on the last project, we said they couldn't be seen or working, but mine is. Is that okay? It didn't say that on this paper, so I didn't know.
It was a loose rubric, wasn't it?
Yes.
Well, there you go. You think it's worth as much as one that's not? I'm not being mean. I'm just saying which one's harder to write. The one that's centered on the original one, it's not. You can make this thing really easy if you center everything on the origin. That reduces a crap load of complexity. But that's also a slight reduction in grade. Is one little thing going to hurt your grade? Probably not.
If I do extra somewhere else, will it even out?
Your grade is based on perceived complex, how complex it is. And the truth is, I won't really know how complex it is until I see everybody else's stuff. You know, if everybody's swimming in the mud and you happen to be on that one little high spot that's not in the mud, then you look really good. That's kind of how it is. So I won't even think about what's complex until I see everybody else's stuff. It'll be the first thing I do is glance at everybody's and kind of get an idea of what y'all have decided is complex and what is not complex. Anyways, if you two are watching at home, tomorrow we'll talk about your project. Hope you drew something. And I hope you're having fun today.